Thank you to our speakers for sharing their perspectives on advancing the quantum economy and strategies to prepare for it. So now moving on to the next session, which is Scalable and Inclusive Quantum Ecosystem, bridging the gap between theoretical possibilities and practical solutions. So we'll be having this session in a different format. We'll have short, quick presentations by our panelists, post which we'll have a small discussions with everyone. So I would like to invite on stage our first panelist, Colonel Kapil Jaiswal, Senior Director, Research, InfoSec, and AIML, and CISO at Ministry of Defense. Please, sir.
Very good afternoon to everyone. So our discussion topic is seeing the practicality of the quantum solutions which is available. Is there something available today? Where are we going? What are the technology trends? So we decided to do this discussion in a slightly different manner. Myself and Dr. Manish, both of us will give a quick presentation and try to generate some ideas from that to see the viability of the technology in the near future. There's always a distant future, 10 years, 15 years down the line. But what are the options? What are the threats? What can happen in near future, next 3 years, 4 years, 2 years? So we would like to have an insight into that. So going down that path, I want to focus, since now we are looking at, aim is to look at a optimal solutions, which is going to be there in near future. We narrow down the agenda. As we go into the discussion subsequently, we will again widen the scope. But in this, I'm just narrowing down the agenda. Once we are looking that present AI and especially LLMs coming in, the cyber threat landscape has evolved. AI has got introduced into the east stage of mid-range attack postures, and combining it within quantum in near future will have the potential which is going to disrupt the systems. However, what's on the positive side? Is this technology evolution which is going to happen, is it going to give us some solutions also? So I look at it from the positive side. I look at it from the blue team perspective. I try to find out that, yes, what are the challenges of detecting and responding to the larger scale attacks on the networks, and can the quantum and AI help us in fighting that in future? Okay, so that's the general trend of this presentation. And okay, it's not, yeah, green is, no. Yeah, it's gone. Yeah, now it's going, okay. Yeah, okay. So the new age of the cybersecurity will have combination of AI and quantum computing in future. However, quantum computer and quantum machine learning will also give us some benefits, okay? The interplay is like this, what I try to brought out. Current AI technologies, DNNs, LLMs, they have a statistical variability. Once presently you are trying to use them for, you say, initiating an automated response to an attack, people are not very confident, okay? LLMs can give us ideas, it can give us suggestions, but to have an automated response, agent kind of a systems, that's slightly still a far time. Also, these models drift as the data on which they are operating itself changes, the nature and the trend of the data. Once it changes, either the model is not able to follow the drift, and in that case, your response is not going to be there. So once you have a critical response has to be initiated, which is based on the premise that once activated, it is going to not affect your system negatively, then there's the issues. So somebody like Jaiswal has said, we are on a journey with AI. As of now, it's a collection of statistical outcomes, his perspective. Anyway, so cyber threat landscape combined with AI machine learning is like this. So you can just go through at each stage of the say Mitra attack model today, you can have AI and LLM contributing to it. Okay, so this is going to, and this is already happening. I'm not saying this is not. One of my friend has a private entrepreneur. He got a mail from his partner saying to transfer certain amount of money to a specific bank account, and it was exactly the way in his Outlook mail account, and it was exactly the way he used to speak to his partner. So this is the kind of personalized attack and the spear phishing attacks which are possible with the LLMs and other things. So with the quantum computing coming in, what are the things which are affected? These are the 5 major things which are under threat. Your cryptographic breakdowns, digital signal forgery, and few other things. Just under our complete private key and digital signature and digital certificate construct is based on the fact that there is a root CA whose public key is known, but his private key is not known to you. And his public private key pair is finally RSA 2048 or a 1024. If tomorrow the root CAs, the private key is calculated by a threat actor which can hire the quantum resource on a quantum computer which is being given by the IBM or Amazon or others, because all these are people are now into business of offering you the quantum capacity in future. Okay, who uses it for what is probably going to be another issues where we are going into ethics in AI. Probably will go into ethics in quantum also to understand what that algorithm a person is putting into a quantum computer, what is supposed to be doing. Today it is not there. You can hire a quantum capacity, you can subscribe to the IBM system, they are giving you 127 qubit processors, and you can run whatever algorithm you want. So the threat, the way it is evolving, it is going to be substantial. But okay, so but quantum computers can't do everything. They can do few things. So these are the few things they can do good. They can do good simulations. They can do good optimizations, especially where the classical computers don't work, that is the non-convex optimizations. In those scenarios where you have multiple minimas, and if you start from one place, you may get stuck into that place and go for the false minima in a multidimensional space. Machine learning. There, quantum computers have a tremendous potential. The reason, a classic classification task in a multidimensional data, once you try to classify the data, the techniques were that if you are not finding into this present dimension, go to the higher dimension, have the second, third, fourth order derivatives of the data, and try to see in that dimensional space if the data is partitioned and there is a clear differentiation is viable. Now, coming to quantum systems, the qubit offers you tremendous amount of higher dimensional capability to process. So those problems which couldn't solve by the quantum classical computers today, where the classical computing algorithms don't see any pattern, the quantum systems in future will see the pattern and they will be able to solve the problems. So let's combine these two and see whether this optimization and machine learning combined can help us to develop a system which can resist or fight the attack being a cyber attack coming onto the say large scale infrastructure. Okay, just some references. Our Mr. Nilesh has already covered the detail, but I'll just bring you out down below. Eagle 127 qubit. This particular processor is now available for hire. You subscribe to the IBM subscription plan, and this particular quantum processor is available. How much it can do? I'll just skip this slide. Okay, how much this can do? So last year, IBM has published this paper. As of now, this particular processor can handle 60 gates operations. That means the quantum volume which you are getting is 127 qubits and 60 operations, 60 gates operation, almost error-free. There are some errors, but they are able to predict those errors. So this particular slide shows there are some errors, but they are able to predict those errors and correct them. So you are getting a quantum volume of 127 qubit by 60 qubits. Their next stage quantum processor 473, which again was referred by Nileshji. This is already there, but as of now, it's not available for subscription model. So they are still testing it. And here what step 1, 2, 3 is the 60 steps which they are able to successfully do. So this much of compute capacity is available even today. And even this is a tremendous capacity if we know how to use it. Just try to understand our processors are still 64-bit processors. It is double that capacity. Its parallel processing capability is double of all our any microprocessor which is existing. Combined it, that qubit can represent multi-dimensional superposition state and carry more information per qubit. This is still, the problem is we still don't know how to actually harvest output of the system. So we are still that boundary of we are able to transfer the classical problem to a quantum domain and solve them. That's still a challenge. And the quantum machine learning, lot of data is now available, lot of models are available. So the translation of problem from classical to quantum machine learning is now easy. The problem of actually transferring the problem from classical to quantum state is the difficult problem. Okay, so just to address that, I will refer to two papers. One came in February 2023, which talked about how to have a autonomous cyber defense agent where you deploy multiple agents across the devices. Each one of them is reporting back to you. As and when the attack start developing. Here I'm not talking about some attack coming on one small company and just attacking 300-400 people. No, we are looking at the attacks which are developing on a kind of a nation states where your hundreds of cities are being targeted, your thousands of critical infrastructure is being attacked. We're looking at that kind of a scenario. So once we go into that kind of a state, so there's some amount of sensors are going to get deployed. However, the attack is not going to come everywhere at one time. Whatever may be the adversary, there is a problem of connectivity, there is a problem of computing resource, there is a problem of bandwidth availability, there is a problem of human resource which can be deployed. So attacks will develop over a period of time with a different phase. Even today, a good attack which say compromises a medium-sized say enterprise also takes few days to launch. It doesn't happen in minutes. Okay. So in this kind of a scenario, the major problem which comes is this attack path. It is estimating the attack path based on the information coming from thousands of sensors. Identifying which one are the real, which are following a particular sequence of actions which are representing an attack. So this is a problem, again a problem, multidimensional problem where you have to find similarity between the, say you have got a million system, thousands are being attacked. The attack vector may be different in time and domain, depending on the what kind of infrastructure it is. If there's a different kind of, one has got a Linux server and also got a series of Windows server, the initial attack vectors may be slightly different. Subsequently, they may go into the major issues, but initially it may be different. So the identification of attack path based on this data. Now, it is a classical non-convex optimization problem, very difficult to solve and complex on the computers. So some people have come up with the method to find the vertex where the attack is happening. So there's another paper. This was actually a thesis, not a paper, which using the machine learning tries to detect this attack frontier. It's called the vertex of this attack. Now, to solve this, as early as May 2024, a hypergraph neural network-based solutions, which has been recommended, which runs multiple neural networks, hypergraphs at multiple nodes, have interconnect between the nodes through a neural network, try to learn the attack, share the model parameters between multiple graphs, and try to detect the attack. Now, if we go actually slightly deeper into this, this is a classical problem which can be translated to a quantum computer and to do this detection of attack surface or the attack vertex in almost real time. Obviously, this cannot be done on a 127 by 60 quantum volume, which is presently available. But I'm working with some people who are academia, but we are saying if you have a 1,000 by 1,000 kind of a computer, quantum volume available to us, this particular thing can be solved. And 1,000 by 1,000, we are not looking, probably another 2 or 3 years, we'll have this kind of a capacity available to us. Okay. So another issue was, okay, the bad actors are getting into it. So what can be done to anti-ransomware? Fine, you encrypted my system. I go and attack, I approach a company which uses a quantum computer to get the keys out of that encryption. Yeah, so there is a full business model of anti-ransomware team using the quantum computers will emerge. Okay, so anti-ransomware, they have to worry about their, they also have to go into the post-quantum cryptography to finally do this kind of a work. But anyway, so that's on the lighter side. So I will not go into this implementation strategy. So idea was, quantum computers are there. It's not something which you're talking in future. So it's already there. 500 qubits, give or take, is what is available today. 100 to 200 depth of the circuits, that is what is available today. That is what is declared. What is not declared, that out of the 35 billion which has been invested into this quantum systems, 15 billion has been invested by China. Where China has reached, we don't know. How much papers they have published? In last 5 years, China has published 13,000 papers in the quantum domain. We have published as a country 2,000. America has published somewhere around 12,000. So that's the amount of focus, energy, and effort is being invested by the world around in this. So there has to be a potential. I think there are much, much brighter people who take this decision of investment, and they are seeing that there is a real potential and value in it. Okay, thank you.
Thank you, Colonel Jaiswal. I would now like to invite Dr. Manish Modani, Principal Solution Architect, NVIDIA, to give the presentation.
May I start? Okay. Okay. Hi, good afternoon and happy quantum. Sorry for this technical glitch. I am from NVIDIA. Would like to talk about quantum computing more. I know here we are talking quantum communication more or cyber security, but they are interrelated, and would like to talk where we are and how we are progressing in this world. One thing is there which everyone says, quantum is a real thing. It is coming. When it is coming and how we are adopting, that is the case. So if we see historically what happened and how architecture evolved, right? Many might be aware, and with me, around 2006, NVIDIA came up with they converted their graphics card into compute. IBM came up with the Blue Gene Q, lightweight processor. Intel came with the Xeon Phi. So they are like a co-processor. All three were co-processor. So you have main processor, CPU, whatever you say. Then we used to have co-processor, which are dedicated for certain tasks. Those architectures were available 2005-06 onward. All companies were trying to demonstrate the advantage of that technology. And they were there. Still, we are using those as a co-processor for everything. But that time, first architecture came. And that architecture being used in 2012 AlexNet competition, and they won the competition, where then we know the deep learning can solve our day-to-day problem, right? So first architecture was available, those algorithms written on those architecture, and then we can see that those real-time problem can be solved through AI, or what we say the part of AI is deep learning. Again, we go forward, we see that generative AI came, or I am sure most of us are using the ChatGPT, right? I myself get the email. Earlier, the student used to write 3-4 line email for internship. Now I used to get 2-page email, thanks to ChatGPT. And then we understand that what is happening. So that's what it is going on. Where I'm coming again, synergy is architecture available. One is writing the code from scratch on the available architecture. Hence, we are able to use ChatGPT. Now you see every company are investing in Gen AI, what Sir said before. They are making their own LLM with some guardrail, with some context length, query, whatever, there's some criteria. But every company is investing in that, right? So architecture was available, and then things are happening now. Now let's go to quantum side, where my analogy says, and I'm very confident on that, systems are coming up, we need to start using those, and we will have quantum advantage. What the meaning of quantum advantage, or what everyone asking when the quantum coming? Quantum is there, people are using it, they are trying to solve the problem. The only discussion point comes is it better than what we are doing with classical? Once we showcase it is better in terms of performance, or we can solve unsolved problem what we can do on classical, then only people say it's a quantum advantage, right? One thing we all talk about RSA 2048, what's our encryption, decryption, and so on. What's the meaning of breaking of those? Just would like to elaborate those. The breaking means if we have the key and we can find 2 prime numbers, the key is multiple of those, that is the breaking. Finding those 2 prime number is the key. Once we have those 2 prime number, anyone can break your key. Now, finding those 2 prime number on classical will take very, very long. That's where we are safe today, right? Now on quantum computer, the Shor algorithm came, and that says finding that would be much easier, much faster. Hence, Shor ka Shor hai, everyone is afraid. But again, I would say, don't be afraid, we are in safe hand. On real quantum computer, my knowledge says, my research, whatever I am reading, only 35 number has been broken. Rest all are simulations, right? So far, and it is going forward, but by that time, either we have post-quantum cryptography or we have classically more mature. So it's a race, it's going on, but we are in safe hand. We should be aware, but we should not make panic, right? So, okay, now one scenario I put as any application, how it will look like in future. And it's all agreed, all researchers agreed on that. What happens is any application right now we start, and I take again reference of ChatGPT or large language model, which is commonly used. Any application you take, which starts generally on CPU, you read the data from any file, read the input and all. Then there is a part of application is a number crunching, where we do our do loop, for loop, or whatever in any language, whatever we do, that is part of number crunching. In end, we post-process the data, and we take that data in our desired format. That desired format could be policy making, could be disaster management, could be medical side or anything, right? So generally that number crunching part, that goes on co-processor, which I mentioned before. Those could be anything, and nowadays we say those are GPUs. So there we can, the Number crunching part offloaded on GPU, rest remain on CPU. So the GPUs is being used as an accelerator, and that's where we have ChatGPT or deep learning quick answers in a given time. Future, what we are seeing is quantum will also work as an accelerator. What it means is, if your application end-to-end, if it has certain part which can exploit the quantum computer, then only the quantum computer will be useful for that. That is one part. Second, quantum computer will not work standalone. It will work with our existing computer, right? So our computer will have part of quantum computer chip, and that will go in that sense. So that is what we are saying, that the quantum computer will work as an accelerator. Right now, those accelerators are GPUs, FPGA, or any coprocessor you take, right? Now with that, the one challenge always what developers are feeling is, the classical computer has to talk with the quantum computer. The classical computer, as before mentioned, it has a bits. Quantum computer has a qubits. They are different analogy. Qubit has 3 key features: superposition, entanglement. So that is the key for that, whereas bits are keep only one state at a time, and then we need so many bits to have that, right? So how they will talk to each other, one application, how they will talk to each other, that's a key question. The second question comes, which is a hardware side more. The qubit can retain their state for many, nanoseconds, or even less than that. In that time frame, the communication has to happen, and then the computation also has to happen. So that is the challenge. That's where we say, even sir was saying 400 qubit system is there. Even if you say last 40 years data, if we take their weather data, suppose I take 40 years weather data, if we take them time series analysis, they represent 1 trillion state, right? In quantum computer, those states can be given only in 30 qubits. Whereas in classical, we need 1 trillion bits or different state. Now, but we are processing those on classical. On quantum, we do not have any algorithm ready, or due to other surroundings like qubit retain their state for limited time, qubits are erroneous, we are not able to exploit the quantum capabilities for those problems. But it is coming up. Drug discovery is the prominent field I am seeing. Even many companies, like including Pfizer and all, they are investing a lot. So I am seeing that drug discovery may come soon with some solution on that. So with that, would like to say, to be quantum ready, what a developer need. Right now, what they need is availability of quantum computer is limited. So they need a platform where they can perform some computations and be ready with the quantum application. Whenever the main actual quantum computer comes, they can run on there. What I mean is, whatever available right now quantum computer, they are in limited, access are limited, and they are costlier as well, right? So the developer need a platform where they can develop a code, and which we call it as a simulations, so they can perform the simulation now and be quantum ready for tomorrow. So, and at NVIDIA, what we are seeing, whatever system you have right now, every institution or every industry, right now they have GPU-enabled system where they do their AI. On that only they can perform the quantum simulations. Today they perform the quantum simulation. The same thing can be run on actual quantum computer tomorrow without changing any application, right? So that way we are trying to make people quantum ready. And for this, we are doing the academic collaboration and so on, so on. I won't go deeper into that, but we have all environment in place. In India also, where various places we are collaborating on that. This is our ecosystem. Almost all the players you will see on quantum computer, we are working with them. I don't want to make it as a advertisement or public that thing, but where I would like to come is, the one thing is, when we run any application, as I said, partly it will run on classical, partly on quantum. So that doesn't mean that classical performance should not be there. So what we are aiming is, classically it should give the best performance, and then quantum it should show the advantage of that. So we support all interoperability, OpenACC, OpenMP, MPI, these are being used on classical, right? How it will work, that I would like to show. Any application, as I said, part of it will run on classical, part of it in quantum. If we see the first part, we know that we are applying some gates, we are manipulating with qubits, that will go on quantum. The bottom side is linear algebra, LU factorization, that will work better on CPU or GPU, whatever our algorithm is, right? So in a code, just we need to define the pragmas. CUDA-Q is for quantum, and rest will remain on classical. And how it will work is, we simply need to compile the application. Our compiler is NVQ++. But with that, if we define cuQuantum, it will run on 2 days system, which is we call that simulation. When we define a flag Quantinum, which is a quantum computer name based on ion trap, it will go there. Now you might be seeing some difference in the results. One is very smooth result, one is scattered. So there, because that run on actual quantum computer, on simulation we do not have any error, or no error correction and so on, right? But the same code, what we developed today, same code can run tomorrow on quantum computer. So that's the mantra, that to be quantum ready. So with that, there are few results. We are better in simulation and speed up. I won't go deeper. One algorithm, again, this is very commonly used, is variational quantum algorithm, where it partly run on classical system, and then partly it goes on quantum. There we need to parameterize the, like Sir said, it's a combinatorial problem or optimization problem. We need to iterate to find the solution, right? It's not a straightforward solution like analytical, you go and one time you get it. It's an iterative solution. So every time we need to define the parameter. For those parameter, it will run on quantum, come back, check on classical what is the results, accuracy, and again it will go back on quantum. So that is variational quantum eigensolver. That is also can be solved, and we have published a paper where we shown that on classical, it takes a CPU, it takes 1600 seconds, whereas if we run on simulation on GPU, it may take only 2 seconds, right? So with that, would like to say that, and in India, various students now started, they started running the large simulations, where the things so far, generally, if anyone knows compute, generally people were running up to 10 qubit, 12 qubit. But now we are seeing people are going up to 50 qubit. Even in this, we went up to 30 qubit. This is the 60 qubit, the Germany lab, and there they could perform the simulation which we could not do on conventional system. So the quantum is being used. Now they are ready to run it on actual quantum, right? So this is the state. So where I was encouraged, come everyone, start working towards to find the quantum enabled algorithm and solution. As a developer, we all need to work. India is known as a developer country. We all should work. Be ready for quantum. It is becoming available day by day. More it will become available. But as a developer, we should be ready with applications. So with that, I would like to conclude. Thank you. Last but not least, this last thing, we are organizing one summit. If anyone would like to join or register, please welcome. That is in Bombay, Geo Convention Center. Yeah. Thank you.
Please take the chair. Now I invite up on stage Colonel Kapil Jaiswal for a quick discussion, and then we'll conclude there. Colonel Kapil and Dr. Manish, such an insightful presentations. I would like to essentially touch base on some of the things that you mentioned, right? So, first question is for Colonel Kapil. So, Colonel Kapil, you interestingly mentioned about essentially ethics in the context of not just AI, but probably very quickly we have to realize ethics in the context of quantum. I think we have already seen essentially IBM doesn't let you use quantum computer, their quantum platform, to break any crypto. But what are some of the ethical frameworks that one needs to be mindful of when someone is planning to use quantum in their in their use cases? Can you throw some light?
So the issue is like this. There are always going to be the bad actors and the good actors. Okay.
Yeah.
Bad actors are mostly very driven.
Yeah.
some very brilliant mind works there. We have to accept the kind of people who actually go into this hacking. They are one of the most brilliant people who are working there.
Yeah.
The aspect of ethics will come because quantum computers on which the meaningful applications or the solutions searching will happen are not likely to be available to small groups. They are primarily going to be either with the nation state, or they are going to be the big our 4 or 5 firms like Amazon, Microsoft, Google, and IBM, and few other people. Now, in that kind of a scenario, and the model which is going to emerge, as Dr. Manish also brought out, the model is going to be hybrid.
Yeah.
Some portion on classical, some portion on quantum. You are switching back and forth into it. So it's like, so today we hire VMs on the cloud. We hire PaaS, SaaS, depending on your thing, or microservices, serverless, different stacks are there. So in future also these services, the quantum resources will become available through these big firms to the users. Now, at that time, what a particular user is using that resource. So that's where the challenge will come. And with all of us know, with the further development in the cryptography, a user can obfuscate the actual intent of the program being given. It will be a homomorphic code kind of a thing may be running. It will be very difficult for the companies to even do a preliminary analysis of what this guy's intention is. It's very difficult to process. So at that time, how do you develop the ethical framework that these resources are not going to be used for? So like Mr. Nilesh also referred that last year paper, which talked about that RSA 2048 can be broken by 372 qubits, error-free qubits. The objection to that paper is actually, Google has published a counter paper, is not on the quantum component of that. It is on the classical component of that paper. So if that quantum component, they also agreeing is right. So the problem is the way it is being translated from classical to quantum. That's where the problem lies. If that classical problem is solved, frankly, you will have a system which can break the RSA 2048. Okay, so again, another scenario which I discussed, that all our security is based on the root CA's secrecy of its public key.
Yeah.
After that, there will be attacks which will be coming on the root CA's. The people will take their public key, try to go to the quantum system, try to compromise their private key, start running the duplicate CA servers. We will not know what has hit us.
Yeah.
Okay,
Yeah.
You can have a website.
Yeah.
It will, the root CA has been cracked, he will link it to another site, it will get certified as a correct link, and you don't know what is hitting you. So now that's a very, how to solve this problem, ethical problem? I think is, as of now, it's still a very, I'll say, emerging research domain. They don't have any clear answers.
Thanks. Dr. Manish, my very quick question for you is essentially, see, look, India also started investing heavily into the whole quantum technologies, right? So essentially, what we've seen is that most of that is primarily going into the academia ecosystem. So what do you think that we should be doing differently so that most of investment that we make into the whole academia turns into actual products very quickly that can be adopted?
So again, I think you were referring to National Quantum Mission.
Yeah.
So there is just now the proposal being reviewed, and they may announce soon the few projects. I was also part of that. So right now the academia is giving more power. Certainly yes, DST asked academia to lead the front, but at the same time they are bringing a Section 9 company based on that, and then the company will drive how the product can make it to TRL level 7, 8 and 9 and go to market, right? So government is aiming for that. Policies are changing, they are increasing. Even if apart from National Quantum Mission, any project you apply nowadays government, generally they are increasing, you should come with a startup. Some startup name should be attached with you. Even call for a startup or only for a startup was there from DST again in this quantum domain.
Has started.
Yeah, ISER Pune, that's a iHub of quantum, and that is driven by DST, right? So government is changing, but still academia and academia objective generally is research, not the product. and what we need in market is a product to be used, right? So that's a difference. They are coming closer, but more to be done, and we are going in that path. I would say I am optimistic on that. Things are changing, because the 10 years back I saw academia is already isolated. As an industry person, if I go there and say no one was there to listen, now at least people are giving me chair and they are listening me. So things are changing. Yeah.
That's good. So I will quickly open the floor for any question. If there's no question, then I'll ask each of the panelists one more question. Is there any question from the audience? Okay. So my next question is for Colonel Kapil on the similar lines, right? So you've mentioned close to $35 billion investment into the whole quantum technologies worldwide. So, and some of that can be accessed, most of that can't be accessed. But what do you think that we should do as a country to leverage this investment that is already made elsewhere, not just in India? And how do we make best use of investment that has already been done by the country?
Okay. So let's first some numbers. Out of this 35 billion which is talked, 15 is by China.
Yeah.
Around 7 or 8 is by US. Then Europe, UK, and some other country, they are around 2 to 3 billion. India and Japan, they are less than 1 billion at the bottom of it. Okay. So number wise, we are not there. Okay. So in the quantum, there are multiple domains. So you have quantum communication, you have quantum computing,
Yeah.
we have quantum materials, quantum sensing. So
Yeah.
these are generally broad 4 domains. Quantum computers, we are lagging behind. The reason is it's a very high capital intensive task. Quantum communications, we are reasonably doing well. Our own startups like QNU Labs is doing reasonably good onto that front. QRNG, hardware QRNG, we are as good as I will say anywhere in the world. QKD experiments on the fiber, we are also comparable.
Yeah.
So that's one field where we have done well, because this required less capital, more of brain power, we are there. Quantum, again, quantum material and quantum sensing, again, these are capital intensive, so that's where we are not doing. Now, if you look at the ecosystem of the quantum in the world, US is doing its own business, Europe has made a consortium, they are keeping the technology together, China is on its own, and rest of the countries are left there to fend for themselves. That's the scenario. Nobody is going to freely exchange technology among each other. I'm telling you, these 3-4 consortiums which has come, they are developing their technology stack and technology, and they want to build their economic ecosystems on top of it and make money out of it in the next 100 years. They are not going to share this technology. You have to find a sweet spot where you can work. So where for India, what's our strength? We have brightest people. We have experience in IT. We have experience in, I will say develop like a space and technology. So we have a core group of people who can undertake, identify problem sets which are not very capital intensive. They are into maybe computing domains, they may be into the quantum error correction domains. That is the places we have to identify and focus on that and invest our time and energy on those.
Yeah.
Catching up, okay, he has made a 127 qubit, we'll make 10 qubit computer, you're not, that it's not making any sense out of it. So it's a, the race has gone too far ahead. We should know, the correct time is NQM is coming, other thing.
Yeah.
So identify where are those sweet spots in each this and try to channelize our energies into those areas.
Okay. Okay. I think we are running short on time, so I will close the session here. Thanks again, Colonel Kapil and Dr. Manish. For me, I think I'm pretty sure that audience have picked up a thing or two that we otherwise wouldn't have. Thank you so much for your time, and I'll just give you a small memento token of appreciation.
So with this, we'll break for our tea break for 15 minutes. Post 15 minutes, we'll start with a final session for this sub-summit, which is crypto agility and quantum resiliency. So I would request you all to join us back again after 15 minutes. Thank you.